Welcome to the making of a real-time strategy game, Part 9. Previously, we made an electrical grid, truck logistical system, robot flocking and aggro, more weapons, an economic system, an attempt to make the AI, minor improvements, and terrain and prompts. This video has a good start with some efficiency work, but then all progress slows down as I get stuck again in not knowing the next step. I start to work on the balance and AI, and eventually I figure it out. A few more minor projects, and the game is ready to make maps. The way multi-meshes normally work is that they have bounding boxes, and either the entire thing is drawn or not. Sometimes, though, that results in the model disappearing when zooming out. There are culling options that can be used to avoid this. When I was looking into why they occasionally disappear, I realized that since I store all the robots in a spatial subdivision, it is easy to do correct frustum culling. First, to generate an axis-aligned bounding box for visibility, the viewport rectangle is obtained. It is a visible rectangle in global screen coordinates. In other words, the 3D coordinates of the camera lens if it was a square. Each of the 4 points of the rectangle are then raycasted to the ground plane using the camera's normal to find where they hit the ground. Those contact points form the bounding box of the ground locations that are visible. This is used to determine if something is visible or not. Sounds complicated, but it's quite simple. After this bounding box is obtained, the quantry is called to return a list of all robots in this bound. It does not traverse the list of all robots, it just copies out the robots in the relevant quadrants. The axis-aligned bounding box is called frustum. It is also used in the game by other systems, in particular the audio and the special effects. I was profiling the code and I realized that the code to load the multi-mesh was a bit slow. In the settings, the multi-mesh is either defined by 12 floats for the transform matrix, plus 4 floats for the custom color, and plus 4 floats for the custom instance, so up to 20 floats. These can be loaded by calling the helper function, set instance transform, color, and custom data, with the relevant index. I learned that these calls are slow probably for 3 reasons. 1, whenever a Godot function is called, it has to invoke a C++ function from the C# code. A function might do extra processing, such as calculating a bounding box for culling, which I do not require it to do. This requires a full transform to be performed rather than just some simple translation, scale, and rotation. I realized it would be quicker to do all the math myself and do only one copy of all the data to the buffer. Depending on the buffer type, either 12 to 20 floats are needed to be loaded per instance. If there is a rotation rather than calculate a transform matrix, only one sine and cos need to be called and can be reused. For scale and translation, similarly, a simple variable copy is enough. The code to do this is simple and ended up running 3 times quicker than using the set instance transform. It is not a large time savings overall, but might as well do it to make things more efficient. The total time of the multi-mesh rendering setup is only a few percentages of one thread, but might as well do it. I added drum robots to the game, which causes nearby robots to move faster. I improved the robot base model. I started with a simple cylinder, then a building, and I kept improving until I got something better. April was off to a good start, but then pretty much nothing happened. I only had 11 days in the log for April. Of the few things I got done, I ported to Godot 4.4 from 4.2. 4.4 uses around 20% less GPU, so it's a good improvement. I added the gearbox and the barrel to the prompts. I reworked some of the prompts and added the garden pads. After profiling, I realized that having the FX cache items all in the game tree was a problem. I fixed this to only having them in the effects in the game tree when they're enabled. After they're done, drawing, that kind of thing, I remove them. I also added a new way for robot bases to send waves. Yeah, that's about it. The lack of progress was for 2 reasons. I simply didn't have anything to do in the to-do list. I was still stuck on not knowing what to do with the AI, and that was the one last big item I needed to get done. There was 1 week early April and 1 week late April, which I didn't do any work at all. There was no log entries. I was also getting closer to the end of development, so I was getting complacent since I thought I would be finishing early. I didn't know map making would take as long as it did. I made some progress early May. I looked at the game balance in terms of the power draw of buildings. I also looked to how to balance the tree economy and the drill mines. Certainly not fun work, but necessary. I worked on a map that tested the economy of the game, and I got full upgrades in around 30 minutes. Well, level 2 upgrades. After playing the map, I realized that the game is a bit slow in the start, but when everything is working, the trees, the mines, the defense, the game is fun. I also made some cosmetic improvements. I realized that having small objects, such as the well, can be hard to see, so putting them on pads improves the contrast. In mid-May, I started testing the robot base mechanics, and after enough testing, I finally got it somewhat to work. I implemented the robot's ability to call for help, and humorously, given the slow robot speed, the help always came too late. So I made a robot jet unit that was faster. I later sped up support units too, like the healer, since it was also too slow to arrive to the battle in time. At this point, I more or less got all the robot base's offensive mechanics to work. The code of the robot bases has been completely refactored and improved by splitting its functionality into several classes. When defining a base, each base has its own unique index that also corresponds to its color. It also has an aggro range and random walk range. The base defines its strength of offense and defense. So how is strength balanced in the game? The entry-level laser does 10 damage a second for 10 energy a second. The first level tank battery has enough to destroy 15 robots. Actually 14 since it cannot completely discharge. It needs to save a little bit for movement. Each robot has 3.5 the base, or nearly 4 times the base, hit points. So why does this matter? A laser can fire for 2 seconds and then it has to recharge. Since the tank has 2 lasers, it can destroy 1 robot per charge cycle. If the laser tank has only tier 1 lasers, the strength of the base's offense or defense corresponds to the battery capacity of all the laser tanks attacking. So it is easy for me to balance the game based on knowing how much battery capacity is possible at each time of the game, such as early game, mid game, late game, etc. Of course, the other weapons are capable of more damage, so this number is just the baseline. For the laser, each time it upgrades, it gets a bit stronger. However, the energy requirement does not. I realized later in the development that if I increase the energy, this makes it harder to sustain fights, which is not that fun. The cannonball also uses a base damage and does a multiple of it. The upgraded types do a larger multiple since the upgrade requires items from 2 trees versus 1, so it should do double. In the code, shrine control is mainly used to get the settings from the map editor and make it available to the inheriting classes. Mob spawning has actual code that selects which robot to spawn. The code has a lookup table with the ratios that select the next units. To add a new robot type to the game, first this requires making the robot model, say in Blender, then adding a class with any unique functionality, adding a multi-mesh, and adding the type to a lookup table in RTS Mob Engine. That's the one that contains the multi-meshes. And lastly, adding it to the lookup table in mob spawning. There is some simple math and some random numbers to select the next robot type. Formation movement is added to the game, getting rid of flocking completely for the trucks. This is the final version in the game. At the time, it was not quite this good. The algorithm is very simple. First, look up the angle of the last pathfinding movement. That is the destination angle. Find the destination location for each truck, given the click location and that angle, well, rotate it 90 degrees, and knowing how many trucks. Trucks can be placed up to 4 across. For each known destination, find the closest truck in the current formation, and that is that truck's destination. However, this does not work in all cases. If the formations are skewed, let's say the formation has truck 1, 2, 3, 4. Sometimes destination 1 will pick truck 2. To solve this, the matching is done twice. once left to right, and once in reverse order. The one with the shorter total distance is used. General improvement in the collision avoidance also improves the formation movement. The original version was not as smooth as this one. The Scouts now have rotating rotors. It is hard to see, but it is there. The cockroaches now have legs that move. Both of these animations use shaders. There's one value I send over for speed. Later on, the base robots would get leg flares to show movement. Obviously, you can see it now because I'm using the final version. The last few days were spent working on the lighting. The light moths that you see in this video are currently not in the game. The moths do a meandering random walk towards any lights. Once they locate a light, they circle around it. Each moth that circles around it reduces the light power's output. After blowing up the moths, the light turns on again. Originally, I was going to have soft fog of war by having the player activate lighting as they explored the map, and the light moths were going to counter this. However, Omnilights can be GPU intensive. Also, the shadows would also become more computationally expensive. Since I cannot have a mechanic that some people will use and some cannot, I decided not to add contested lighting to any maps. I might reintroduce it later since it is a fun mechanic. The current lighting has a single directional light when the batteries have power, and when the batteries are at zero, a backup Omni light near the base gives a minimum amount of light to help the player get the power going again. I have to reflect what happened in April to May. I once again got stuck and had a few weeks where I did not do any work. But how did I get unstuck? I think I was asking the wrong question. How do I make a fun AI that makes the game fun? Instead, when I started to experiment with maps, the question was, how does the AI make this map fun? Instead of having to theory craft how the game works and being stuck, what worked was making scenarios, playing them, and working on it to make it fun. Eventually, I figured it out. Perhaps in hindsight, I could have saved maybe a month or two. After around a year and 266 days of work, I'm finally ready to make maps. Thanks for watching.